Light travels at exactly 299,792,458 meters per second. But this isn't just the speed of light. It's the cosmic speed limit built into the very fabric of space-time. Nothing, not even the fastest particle or the most powerful force, can move faster. This limit isn't an arbitrary rule. It's a fundamental feature of reality itself, woven into the laws that govern energy, matter, and causality. If anything could exceed light speed, cause and effect would break down. Messages could arrive before they were sent, and time itself would lose meaning. The speed of light isn't merely about light, it's about how space and time interact, defining the ultimate pace at which information and influence can travel through the universe. So watch this video till the end and subscribe to the channel. Let's start. When we trace the origins of why light's speed is the universe's limit, we arrive at a moment in the 1860s when science stood on the edge of something extraordinary. Before Einstein, before relativity, there was James Clerk Maxwell, a quiet Scottish physicist who saw deeper into nature's symmetry than anyone before him. At that time, electricity and magnetism were treated as separate forces, mysterious yet immensely useful. Sparks and lightning on one hand, magnets and compasses on the other. They seemed to belong to different worlds, but Maxwell believed there had to be a deeper unity behind them, something elegant and mathematical that could explain both. Through a series of brilliant insights, Maxwell developed a set of equations that unified electricity and magnetism into one grand framework: electromagnetism. His work showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, a self-sustaining loop of energy. When he wrote these relationships down, something astonishing emerged. From the mathematics themselves, without any assumption about light at all, there appeared a wave, a ripple in the electromagnetic field that would propagate through space. And when Maxwell calculated its speed, he found a number that matched the best measurements of the speed of light. It was as if nature had left a clue written in the language of mathematics, whispering that light itself is an electromagnetic wave. This realization transformed our understanding of reality. Light was no longer a mysterious, weightless substance that simply was. It was the motion of fields, electric and magnetic, intertwined, dancing through space at a constant speed dictated by the very laws that define how those fields behave. But the real wonder wasn't just that Maxwell's theory explained light. It was that the speed of these waves wasn't determined by any external reference, not by the movement of a source or the observer, not even by some physical medium like air or water. Instead, the speed was built into the equations themselves, the constants describing how strongly electric and magnetic fields interact produced, by their very nature, a single universal speed, the same everywhere for everyone. This suggested something deeply profound, that light speed wasn't merely a property of waves, but a fundamental feature of space itself. In Maxwell's framework, the vacuum, empty space, wasn't truly empty. It had structure, it had properties, it had the capacity to support electromagnetic waves. The nothingness of space wasn't nothing at all. It was the stage upon which the drama of light and matter played out. Yet this elegant revelation also created a troubling paradox. If light always moved at this fixed speed, the question naturally arose: relative to what? In Newton's universe, motion was always relative to something else. A ship moves through water, the Earth moves through space. So physicists reasoned light must also move through some invisible medium, something that fills the cosmos and carries these waves. They called it the luminiferous ether. According to this view, the ether was like a cosmic ocean through which light rippled. The Earth, moving through this ether as it orbited the Sun, should experience a sort of ether wind, changing the apparent speed of light depending on direction, much like how sound waves seem faster or slower depending on whether you move toward or away from their source. The logic was solid within Newtonian thinking, and for a time, most scientists accepted the ether as fact, even though it could not be seen or measured. But a storm was brewing beneath the surface of 19th century physics. Maxwell's equations, though dazzlingly successful, quietly defied the principles of classical mechanics. In Newton's world, if you chase a moving object, its speed relative to you changes. Yet Maxwell's waves didn't seem to care about motion. They insisted on a constant speed regardless of your frame of reference. Something wasn't fitting. Physicists found themselves in an intellectual standoff between the old and the new, between a universe where motion was relative and one where the speed of light seemed absolute. The stage was set for one of the most famous and consequential experiments in scientific history, designed to settle once and for all whether this mysterious ether truly existed and whether light speed really was universal. And that experiment, conducted in 1887 by Albert Michelson and Edward Morley, would shatter centuries of assumptions and open the door to the revolutionary ideas that would follow. It was an experiment that would show, in the most precise way then possible, that light speed is not just constant, it is unchangeable no matter how fast you move through space. And from its quiet, null result, Einstein would later find the clue that would rewrite our entire understanding of time, space, and motion itself. Maxwell's discovery was breathtaking, but it also opened a rift in physics so deep that it nearly split reality itself. His equations had revealed that light always moves at the same speed, regardless of who measures it or how fast they're moving in. But according to the framework of Newtonian physics, that simply couldn't be true. In Newton's world, motion was always relative to something else. A ship moves through water, the Earth moves through space. So physicists reasoned, light should behave the same way. If a beam of light travels past you at its constant speed and you start moving toward it, Newtonian reasoning says you should measure it as coming at you faster. Likewise, if you move away from the beam, you should measure it as slower. But Maxwell's equations didn't allow that. No matter how fast you moved, toward the light or away from it, the equations demanded that light speed remain exactly the same. That inconsistency created a profound problem. Either Maxwell's theory was incomplete or Newton's conception of motion and space itself was wrong. For 200 years, Newton's laws had described everything from falling apples to orbiting planets with flawless precision. They were the foundation of all physics. To question them was to question the very framework through which we understood the universe, and yet the math refused to bend.
So physicists began searching for an explanation that could preserve both worlds, one that would keep the comforting certainty of Newtonian mechanics while respecting the strange constancy hidden in Maxwell's equations. The idea they clung to was the luminiferous ether, that invisible medium they believed filled all of space. It would serve as the universal reference point, the absolute background through which light waves moved. In this view, light always traveled at the same speed through the ether, but if you were moving through that ether, you would experience the light differently. Your motion relative to the ether would alter your measured speed of light, just as moving through air affects how you hear sound waves. The ether seemed like the perfect solution, elegant, invisible, and obedient to Newton's worldview. But there was a catch. If the ether existed, it should be detectable. The Earth moves around the sun at tens of thousands of kilometers per hour, so we should constantly be sweeping through the ether, creating an ether wind. That wind should slightly change how light behaves depending on the direction it travels. Just as a swimmer feels resistance when swimming upstream and less when going downstream, light should appear to move faster or slower depending on whether it's moving with or against the ether. This prediction opened the door for experimentation. If scientists could measure that tiny change in light speed, they could prove the ether's existence and restore harmony between Newton and Maxwell. But if they couldn't, if the speed of light turned out to be the same no matter what, then the entire Newtonian concept of absolute motion would begin to crumble. The late 19th century became an era of mounting tension between theory and observation. Physicists trusted Newton, but they also trusted Maxwell's mathematics, which kept proving astonishingly accurate. Both couldn't be entirely right. It was like having two perfect maps of the same terrain that refused to line up. Somewhere, something fundamental had to give. Then, in 1887, Albert Michelson and Edward Morley set out to perform one of the most precise experiments in scientific history. Their goal was simple, but profound: to measure the difference in the speed of light in different directions as Earth moved through the supposed ether. They designed a device of extraordinary precision, capable of detecting the slightest variation in light's behavior. If the ether was real, their instrument should have caught it without question. But when they conducted the experiment, the result shocked the world. There was no difference at all. Light speed was exactly the same in every direction, no matter how the Earth moved. The ether wind, the invisible flow that everyone assumed must exist, simply wasn't there. This was not just an experimental surprise. It was a conceptual earthquake. The foundation of Newtonian mechanics, that motion and velocity were always relative to something, was suddenly in doubt. If there was no ether, then what was light's constant speed relative to? It couldn't be relative to space because, in Newton's model, space was just an empty passive stage. It couldn't be relative to the observer because the Michelson-Morley experiment had shown that no matter how fast you moved, you always got the same answer. The physics community was left in disarray. Some tried to patch the theory, suggesting the ether somehow contracted objects as they moved through it, conveniently hiding its effects. Others proposed that the ether was undetectable by design. But none of these explanations truly solved the paradox. They only postponed it. A new way of thinking was needed, one that would break completely with Newton's concept of absolute space and time. Someone had to look at the situation not as a contradiction to be patched, but as a clue to something deeper. That someone, years later, would be a 26-year-old patent clerk in Switzerland who dared to suggest that it wasn't light speed that needed explaining, it was our very understanding of space and time themselves. By the late 19th century, the idea of the luminiferous ether, an invisible medium filling all of space, had become almost a certainty among scientists. It was the missing puzzle piece that seemed to reconcile Maxwell's constant speed of light with Newton's laws of motion. If light were a wave, then it must have something to wave through. Water carries ripples, air carries sound, surely space must carry light. The ether, subtle and undetectable, was believed to be that universal ocean stretching across the cosmos. But even a subtle ocean should leave traces of its presence. If the Earth moved through this ether as it orbited the sun, there should be a detectable ether wind. Just as a moving car feels the rush of air outside on a still day, the Earth's motion should create a tiny breeze in the ether, one that would slightly alter how light behaved depending on direction. Light moving with the ether wind would appear to travel a bit faster, while light moving against it would seem slower. To test this, two physicists, Albert A. Michelson and Edward Morley, designed one of the most precise experiments ever attempted. Michelson, a brilliant experimentalist with a mind for precision, had already been refining a technique to measure incredibly small differences in the speed of light. Together with Morley, they constructed an instrument called an interferometer, a device so sensitive it could detect changes in distance smaller than a fraction of a wavelength of light.
The principle was elegantly simple. A single beam of light was split into two identical beams. One beam was sent along the direction of Earth's motion through the ether, while the other traveled perpendicular to it. After reflecting off mirrors, the beams were recombined. If the Earth was indeed moving through the ether, the light traveling upstream and downstream should take slightly longer to complete its journey than the one traveling across the current.
When the two beams met again, that tiny difference in timing should create a pattern of light and dark fringes, an optical interference pattern that would shift as the device was rotated. The experiment was set up in Cleveland, Ohio in 1887 on a large stone slab floating in mercury to minimize vibration. Michelson and Morley took painstaking measurements at different times of day and throughout the year, expecting the direction and speed of Earth's motion through the ether to change slightly with the planet's orbit. By every reasonable calculation, the effect should have been small but detectable. And then came the shock. Nothing happened. No matter how the instrument was turned, no matter when the measurements were taken, the interference pattern stayed perfectly still. The light always took the same amount of time to travel both paths. The expected ether wind simply wasn't there. This null result was so astonishing that Michelson himself initially suspected an error. He refined the apparatus, improved the precision, and repeated the experiment. The outcome was the same. Light speed was identical in every direction, regardless of how Earth moved. It was one of those moments in science where silence speaks louder than discovery. The ether, that all-pervading cosmic substance, seemed to vanish without a trace. The implications were staggering. If there was no ether, then what was light actually moving through? And if light speed was constant regardless of motion, then something far deeper was wrong with the foundations of classical physics. In Newton's universe, there was always a reference frame, an absolute stage against which all motion could be measured. But Michelson and Morley's result implied that no such stage existed. Space wasn't filled with a medium, and light didn't need one. Its speed was simply the same for everyone, everywhere. Many scientists were unwilling to abandon the ether so easily. Some proposed desperate fixes. Maybe the apparatus itself contracted slightly as it moved through the ether, hiding the expected differences. Others speculated that the ether was somehow dragged along with Earth, making it undetectable. These explanations patched the hole but didn't solve the underlying contradiction. Despite its failure to detect what it sought, the Michelson-Morley experiment became one of the most important experiments in history, precisely because it failed. Its null result was a quiet revolution, a sign that the universe didn't behave the way everyone had assumed. It pointed toward a reality where space wasn't a passive backdrop and time wasn't absolute, where the very geometry of the cosmos had to be reimagined. For years, though, the result sat as an unresolved paradox. Scientists could measure the constancy of light speed, but they couldn't explain it. The equations of motion and the equations of electromagnetism still refused to coexist peacefully. Something fundamental was missing, a new way to think about motion, time, and the very nature of reality. Then, in 1905, a young man working in a Swiss patent office would finally bring the pieces together. He realized that the problem wasn't with light or with motion. It was with our assumptions about space and time themselves. Instead of trying to fit light's constancy into the old framework, he tore the framework down and built something entirely new in its place. That man was Albert Einstein, and his revolutionary insight would change everything, giving us a new picture of the universe where time, space, and motion were inseparably linked by that same unyielding constant, the speed of light. When Albert Einstein entered the stage of physics in 1905, the field was teetering on the edge of contradiction. The results of the Michelson-Morley experiment had left scientists deeply unsettled. Light speed seemed fixed, yet the laws of motion demanded it change depending on an observer's movement. For 2 decades, the paradox had resisted every attempt at reconciliation. Most physicists were trying to protect the old worldview by tweaking it, adding layers of theoretical scaffolding to hold up the idea of the ether. But Einstein did something radical. Instead of trying to save Newton's universe, he asked a simple but daring question. What if the experiment isn't wrong? What if light speed really is constant for everyone, no matter how they move? It was the kind of question that only someone unburdened by academic dogma could ask.
Einstein was not a professor or an experimentalist. He was a 26-year-old patent clerk in Bern, Switzerland, working long days reviewing mechanical designs and spending his nights thinking about the deep mysteries of physics. He had a gift for seeing through complexity to the heart of the problem. And for him, the heart was clear. The laws of physics should be the same for all observers, no matter their motion. From this conviction, Einstein built two revolutionary postulates, simple yet world-shattering in their implications.
First, he declared that the laws of physics are identical in all inertial frames of reference, meaning that there is no privileged rest frame in the universe. Whether you are standing still, flying in a spacecraft, or gliding through interstellar space, the same physical laws apply. There is no cosmic background like the ether against which motion can be measured. Motion is purely relative. Second, he proposed that the speed of light in a vacuum is the same for all observers, regardless of how fast they are moving or how the light source is moving. No matter who measures it or where they are, light always travels at that same fundamental speed, about 299,792,458 meters per second. This second postulate was the real shock. It defied all intuition. How could two observers moving relative to each other both measure light's speed as the same value? In the Newtonian view, if you chased after a beam of light, you should see it slow down slightly. If you ran toward it, it should appear faster. Einstein's theory said the opposite. You could race at half the speed of light, or even 9/10, but the light ahead of you would still move away at full speed. This paradox could only make sense if something else, something deep, gave way. And that something was the very fabric of space and time. Einstein realized that in order for light speed to remain constant for everyone, space and time themselves can no longer be rigid and absolute. They had to be flexible, intertwined dimensions that shift depending on motion. Time would not flow at a single universal rate, and distances would not remain fixed. They would both stretch and compress to preserve the constancy of light speed. This was the birth of special relativity, a theory that redefined what reality meant. In Einstein's universe, space and time are not separate entities ticking away independently. They form a single unified fabric called space-time. And what one observer calls space and time may look different to another. The faster you move through space, the slower you move through time. The universe balances these two motions perfectly so that the combined speed through space-time always equals the speed of light. To Einstein, this wasn't just mathematics, it was a new way to understand existence. The constancy of light speed wasn't a problem to be explained, it was the fundamental principle upon which the rest of physics had to be built. And by making it a postulate rather than an anomaly, he turned what was once a paradox into the cornerstone of modern physics. The implications were staggering. Time could no longer be universal. Two people moving at different speeds could genuinely experience different durations for the same event. Distances could no longer be absolute either. Motion could literally alter the way space itself is measured. Even simultaneity, the simple idea that two events can happen at the same time, was shattered. What is simultaneous for one observer might not be for another. Einstein had revealed a cosmos where space and time were woven together in an intricate dance, constantly reshaping themselves depending on motion. The speed of light was the cosmic referee, ensuring that all observers, no matter how fast they moved, would agree on one thing: the speed limit of the universe. It's difficult today to grasp how profoundly this overturned centuries of belief. Before Einstein, time was thought to be an invisible river flowing steadily everywhere in the universe. After Einstein, time became part of a grand, malleable fabric that could twist, stretch, and even slow down. And all of it arose naturally from the simple decision to treat the speed of light as absolute, not an effect to explain, but a truth to build upon. Einstein's paper, titled On the Electrodynamics of Moving Bodies, was published in 1905, a year now known as his Annus Mirabilis, or Miracle Year. It didn't just solve the paradox that had haunted physics since Maxwell, it transformed the way we think about everything,
from the ticking of clocks to the structure of the cosmos itself. With that leap, the ether vanished forever, and in its place emerged the far more beautiful and mysterious reality, a universe where space and time themselves bend to keep the speed of light constant, ensuring that causality and the fabric of reality remain intact. This revelation was only the beginning. The next step would be even more astonishing: the realization that space and time weren't just linked, but truly inseparable, forming a single, unified entity that defines every motion, every event, and every possibility in the cosmos. Einstein's revolutionary insight didn't just change how we measure motion, it changed how we perceive existence itself. Before his 1905 breakthrough, space and time were thought of as entirely separate realms. Space was the three-dimensional stage upon which the universe played out, and time was the invisible clock ticking evenly everywhere. The two never touched, but Einstein's special theory of relativity tore down that wall and revealed something profoundly deeper. Space and time are not distinct. They are two sides of the same cosmic fabric. This unified entity is what we now call space-time. It's a four-dimensional continuum where the three familiar dimensions of space, length, width, and height, are woven together with the dimension of time into one inseparable whole. It's not that time is just another spatial direction, it's fundamentally different yet connected. Together, these four dimensions define the geometry of the universe itself. To visualize this, imagine space-time as an enormous, invisible fabric stretching across the cosmos. Every object, a planet, a star, even you sitting right now, exists as a kind of thread woven into that fabric. When you move, you aren't just moving through space. You're tracing a path through space-time, what physicists call your world line. Every second, every step, every heartbeat is a point along that path. Now here's where Einstein's insight becomes truly mind-bending. Motion through space and motion through time are two aspects of the same thing. You can think of each object as always moving through space-time at one constant total speed, which is the cosmic speed limit, the speed of light. This doesn't mean everything moves through space at that speed. Most of what we perceive as stationary, like a person standing still, is actually moving entirely through time instead. For example, right now as you sit reading this, you're not traveling through space at any noticeable velocity. But in Einstein's view, you are racing forward through time, second by second, moment by moment. Your motion through time is at its maximum because your motion through space is minimal. The faster you begin to move through space, the more of that total space-time motion must shift away from the time direction. As a result, your passage through time slows down. This trade-off is one of the most elegant consequences of relativity. The universe enforces a kind of balance. The more you move through space, the less you move through time. It's as if all things in the universe have a fixed allowance of motion through space-time, and the speed of light defines that allowance. Nothing can exceed it because doing so would require moving through both space and time in a way that breaks the geometry of reality itself. So when an object accelerates and approaches the speed of light, time for it begins to slow down relative to an outside observer. Its clock ticks more slowly. From the traveler's own perspective, everything feels normal. Their heartbeat, thoughts, and sensations flow as usual. But to the outside world, their time stretches, dilates, and begins to nearly stop. This isn't an illusion. It's a real physical effect, one confirmed by countless experiments with high-speed particles and precision atomic clocks aboard jets and satellites.
At the same time, distances in the direction of motion begin to contract. From the traveler's perspective, the universe around them compresses in length as their speed increases. This dual effect, time dilation and length contraction, arises naturally from the geometry of space-time. It's the universe's way of maintaining one unbreakable rule. No matter who measures it, no matter how fast they move, the speed of light remains constant. Think of space-time like a tightly woven net. You can move your hand along one thread, space, or down another, time, but the total motion through the net can never exceed a certain combined limit. Light, being massless, takes the extreme path. It moves entirely through space and not at all through time. That's why, from the perspective of a photon, no time passes. A beam of light emitted from a distant galaxy and received billions of years later experiences that journey as instantaneous because it doesn't travel through time the way massive objects do. Everything else, planets, particles, humans, lives below that limit. We are bound to space-time's geometry. The faster we go through space, the slower our internal time flows. The faster we race forward in time, the less we move through space. The universe keeps the total constant, and the constant is c, the speed of light. This interplay between space and time isn't just an abstract concept, it's the foundation of our reality. It explains why GPS satellites need to adjust their clocks to account for both their motion and their altitude. It's why particles created in high-energy accelerators live longer than they would at rest. And it's why, as strange as it sounds, time is not an absolute universal rhythm, but a personal experience shaped by motion. Einstein's unification of space and time revealed that what we once thought were separate domains, where and when, are actually intertwined threads of a single cosmic tapestry. It means that every event in the universe exists as a point in spacetime connected by the speed of light, the ultimate measure of how one event can influence another. And from this understanding comes a profound truth. The speed of light isn't just a limit for motion, it's a limit for causality itself. It dictates which events can affect which others and defines the boundaries of what is physically possible. But before we reach that deeper philosophical territory, there's another side of relativity to explore. What happens to time itself as we approach that ultimate speed? Because in the realm near light speed, time begins to behave in ways that defy all common sense, and yet remain perfectly real. As Einstein's ideas about space-time settled into the scientific world, one of the most astonishing and unsettling consequences began to emerge. Time itself is not absolute. It doesn't flow at a single universal pace everywhere in the cosmos. Instead, the passage of time depends on how fast you move through space. The faster you go, the slower your clock ticks. This effect is called time dilation. And it's not a theory in the abstract sense. It's a measurable, real feature of the universe. To grasp it, imagine two people. One stays on Earth and the other boards a spacecraft capable of traveling close to the speed of light. From the astronaut's perspective, everything inside the ship feels perfectly normal. The clocks tick, the heartbeat pulses, thoughts and sensations unfold just as they should. But from the point of view of the person left behind on Earth, those same clocks aboard the ship are ticking more slowly. The astronaut's entire experience of time has slowed down compared to everyone remaining at rest. This is not just a trick of perception. It's a fundamental consequence of the geometry of spacetime. The faster something moves through space, the less of its motion budget is left to move through time. The universe keeps that total constant, as though space and time were locked in a delicate seesaw balance. Here's the incredible part. This has been confirmed again and again in real experiments. In the mid-20th century, physicists sent atomic clocks on high-speed jets around the world and compared them to identical clocks that stayed on the ground. When the jets returned, their clocks were behind by exactly the amount Einstein's equations predicted. The same happens in orbit. GPS satellites, zipping thousands of kilometers per hour around Earth, experience time slightly slower than we do on the surface. Engineers must correct for this effect continuously, or GPS navigation would drift by kilometers each day. To make sense of it intuitively, imagine you're watching a spaceship fly past at an incredible speed, say 99% of light's velocity. You look through a telescope and see the clock on its control panel. You'd notice that the seconds on that clock tick by sluggishly. What seems like 1 second aboard the ship might take 7 seconds to pass for you. For the astronauts, though, nothing feels strange. Their heartbeats, conversations, and ship systems all seem perfectly normal. It's the outside world that appears slowed down to them. This symmetrical strangeness leads to one of the most famous thought experiments in physics, the twin paradox. Picture twin siblings. One stays on Earth, the other boards a spaceship and travels to a distant star at near light speed and then returns. Because time aboard the moving ship runs slower, when the traveling twin comes back, they've aged far less than the one who stayed home. The difference isn't an illusion or a trick of observation, it's real. If one twin left Earth at, say, 99.999% of light speed for what felt to them like 5 years, they could return to find that decades or even centuries had passed on Earth. The paradox gets its name because at first glance, it seems as though the situation should be symmetrical. Each twin sees the other as moving, so shouldn't each age less? The resolution lies in the fact that the traveling twin must accelerate. They turn around, change direction, and come back, breaking the symmetry. The twin on Earth remains in one frame of reference, while the other leaves it, turns, and returns. Time dilation, therefore, isn't just a matter of relative motion, it's rooted in the geometry of each twin's path through space-time. Now, if we push this idea further, if we imagine accelerating closer and closer to the speed of light, time slows down more and more dramatically. At 99% of light speed, time for you flows at less than half the rate it does for someone at rest. At 99.99%, only a fraction of a second passes for you, while minutes or hours pass elsewhere. And if you could somehow reach the speed of light itself, which, as we'll later see, is impossible for anything with mass, something extraordinary would happen. Time would stop altogether. From light's point of view, there is no passage of time. A photon emitted from a distant galaxy billions of years ago and absorbed by your eye today experiences that entire journey as instantaneous, because it doesn't travel through time the way massive objects do. Everything else, planets, particles, humans, lives below that limit. We are bound to space-time's geometry. The faster we go through space, the less we move through time. Einstein's revelation that time could bend and stretch depending on motion forever changed our understanding of the universe. It means that there is no single now shared by everyone, everywhere. Each observer carries their own timeline, their own rhythm of existence, and those timelines can diverge in profound ways. This also redefines what we mean by the word future. Because if two observers can disagree on how much time has passed between events, then their perception of what lies ahead and behind can differ too. The faster you move, the more your personal experience of time diverges from the rest of the cosmos. Time dilation, therefore, isn't merely a curiosity, it's a direct window into the way space-time protects its deepest law, the constancy of light speed. The universe stretches and compresses time itself to preserve that limit. The faster you go, the more time must slow down for you, ensuring that the speed of light can never be surpassed. It's one of nature's most astonishing trade-offs. The price of moving faster is living slower. At the extreme, motion through space becomes so great that motion through time nearly vanishes.
But time isn't the only thing affected by near light speed. Space itself begins to change too. Just as time stretches for the traveler, distances in their direction of motion begin to shrink. This effect, length contraction, is the spatial counterpart of time dilation, and together they reveal just how deeply motion reshapes the universe around us. As we continue our journey through Einstein's world, we encounter another phenomenon as strange and profound as time dilation: length contraction. It's the idea that space itself, like time, is not fixed and rigid, but can shrink depending on motion. When an object moves close to the speed of light, it physically contracts. It becomes shorter along the direction of its motion. To someone watching from the outside, a speeding spaceship would literally appear squashed, as though space were folding around it. At first, this sounds absurd. How can something solid with a definite size simply shrink because it's moving? But within the framework of relativity, length contraction is not an optical illusion or a trick of perspective. It's a real and necessary feature of the geometry of spacetime. It's nature's way of preserving the cosmic speed limit. To understand why, let's recall what time dilation taught us. When you move faster through space, you move slower through time.
But since the universe insists that the speed of light must always remain constant, space and time must adjust together. If time slows down for a fast-moving object, then space, the very distance the object must travel, must also change to keep everything in balance. This means that for the traveler, distances ahead contract. The universe literally shrinks in the direction they're moving. Here's a simple way to picture it. Imagine a spaceship traveling at 99% of the speed of light toward a star 10 light years away. To an observer back on Earth, the journey should take a little over 10 years. But for the astronauts aboard the ship, their clocks are running slower because of time dilation. They're experiencing time at a reduced rate. If the distance to the star remained 10 light years for them, this mismatch would make the laws of physics inconsistent. So relativity resolved it elegantly. For the astronauts, the distance itself shortens. Maybe the star now appears only a few light years away, allowing the trip to be completed within a few years of their time. Everyone's observations remain consistent within their own frame of reference. For those on Earth, the ship's clocks tick slowly, but the distance remains 10 light years. For those aboard the ship, their clocks run normally, but space itself has contracted. Neither is wrong. Each is simply seeing reality through their own slice of space-time. This interplay between shrinking space and slowing time ensures that the speed of light remains the same in all frames of reference. It's as though the universe itself reshapes to keep the rules unbroken. Motion doesn't just affect how we experience time, it changes the very shape of reality. Now, imagine pushing this to the extreme. As an object moves faster and faster, its contraction becomes more dramatic. At 99.9% of the speed of light, distances in front of it are reduced to a fraction of their normal length. At 99.999% of the speed of light, they shrink to almost nothing. And if, in theory, you could reach the speed of light itself, the contraction would become absolute. The distance in the direction of motion would collapse to zero. That means for something traveling at light speed, the entire universe in the direction of motion would compress into a single point. From light's perspective, if we could imagine it having one, there would be no distance to cross at all. The journey from any point to any other would be instantaneous, but there's a catch. Such a state is impossible for anything with mass. Here's why. As you accelerate, your energy increases, and in relativity, energy and mass are two forms of the same thing. More energy means more effective mass. The faster you move, the heavier you become in terms of inertia. Approaching light speed, your energy requirement soars exponentially, and your mass becomes effectively infinite. To actually reach light speed, you would need infinite energy, a physical impossibility. The reason is simple yet profound. As you approach that ultimate speed, not only does your time nearly stop, but the universe itself flattens in your direction of travel. Space and time simply can't stretch further without tearing the laws of physics apart. For light, which has no rest mass, this isn't a problem. Photons always move at the cosmic limit because they are born without the weight that would slow them down. They don't experience time or distance in the way massive objects do. They exist on the razor's edge of space-time, where motion through space is total and motion through time is non-existent. For them, the concept of travel loses meaning. Their emission and absorption are two ends of a single instant. But for anything with mass, from a grain of dust to a galaxy, the story is different. We can move faster and faster, but we can never break through that final barrier. The closer we get, the more energy it takes, the shorter the distances appear, the slower time flows, until the very structure of space-time itself pushes back. The cosmic speed limit is not a wall we can crash through, it's the fabric that defines reality. This built-in limit has extraordinary consequences. It keeps the universe consistent, prevents paradoxes, and defines what can and cannot influence what. Without it, cause and effect would lose their meaning, and the chain of time itself could unravel. So while time dilation shows how motion slows your journey through time, length contraction shows how space ships your journey through space. Together they reveal that space and time are inseparable, each bending and flexing to preserve the constancy of light speed. But this interplay of shrinking space and slowing time leads to another remarkable realization. As we move faster and our energy increases, we find that our mass, our resistance to acceleration, also grows. This mass increase is the next key to understanding why nothing with substance can ever reach light speed, no matter how much power or technology we throw at it.
When Einstein unified space, time, and motion under the same roof, he discovered something that would forever change our understanding of matter itself. It wasn't just that time slows and space contracts as you move faster, it's that mass and energy are two sides of the same cosmic coin. The faster you move through space, the more energy you possess, and as that energy rises, so does your effective mass. This realization leads to one of the most iconic and profound relationships in all of science. Energy equals mass times the square of the speed of light. This simple-looking relationship tells us that even a tiny amount of mass holds an enormous amount of energy. It also tells us that as an object speeds up, its energy, and therefore its relativistic mass, increases. The faster you go, the harder it becomes to keep accelerating, because every bit of added energy goes into making the object heavier in a relativistic sense. This isn't the kind of heaviness we feel with gravity, it's resistance to acceleration, a kind of cosmic inertia that grows ever stronger the closer we approach light speed. To picture this, imagine pushing a shopping cart across a flat floor. At first, it moves easily. A gentle shove sends it rolling. Now imagine that with each push, the cart somehow becomes heavier, not because more stuff is added, but because the faster it moves, the more it resists further acceleration. The harder you push, the less effect your effort has. By the time it's racing near light speed, it's as if the cart weighs millions of tons. To double its speed, you'd need far more energy than before, an amount so vast that even the combined output of every star in the galaxy wouldn't be enough. This is what happens with any object that has mass. As it accelerates, its kinetic energy increases, and that energy adds to its total mass. Near the speed of light, the mass grows so rapidly that it approaches infinity. And because it would take an infinite amount of energy to accelerate something with infinite mass, no object with mass can ever reach the speed of light. It's not just practically impossible, it's fundamentally forbidden by the structure of the universe. This growing inertia is one of nature's most elegant safeguards. It ensures that the speed of light remains the ultimate limit, not because of some arbitrary rule, but because the universe's own geometry enforces it. The more energy you pour into motion, the more nature resists your attempt to cross that final threshold. The energy you add doesn't increase your speed linearly. It increasingly goes into warping time, contracting space, and boosting your relativistic mass. For humans, who live at speeds where relativity's effects are almost invisible, this relationship feels abstract. But in the subatomic world, where particles routinely move at a significant fraction of light speed, it becomes vividly real. In giant particle accelerators like the Large Hadron Collider, protons are propelled around the ring nearly 27 kilometers wide at speeds exceeding 99.999999% of light speed. The energy required to make them just a tiny bit faster is enormous. In fact, for every increase in velocity, the energy input grows exponentially. The closer those protons get to light speed, the more their effective mass skyrockets, demanding absurdly high energy just to gain the next microscopic fraction of speed. Even with the most powerful technologies we can imagine, we're only scratching the surface of this boundary. At light speed itself, the equations break down. Time would stop, distances would collapse, and the energy required would reach infinity. The very concept of acceleration loses meaning, because the laws of physics prevent any further increase. It's as though the universe has drawn a hard line through the fabric of spacetime and said, you may approach, but never cross. Einstein's equation also revealed something even more profound. Mass is energy, and energy is mass. They are interchangeable. When matter is destroyed, say in a nuclear reaction, its mass doesn't vanish. It transforms into pure energy. This principle powers the sun, where hydrogen atoms fuse into helium, releasing light and heat that sustain life on Earth. It also underpins the destructive force of atomic bombs, where even a small amount of matter converts into enormous bursts of energy. Every flash of light, every chemical reaction, every heartbeat and flicker of a star is a testament to that equivalence. But the reverse is also true. Energy can create mass. In high-energy collisions, particles can spontaneously appear out of pure energy, provided there's enough to meet the mass-energy balance. The universe itself, born in the Big Bang, seems to have followed this rule.
vast amounts of radiant energy cooling and condensing into the matter that now fills the cosmos. This interconversion between mass and energy gives the universe an extraordinary symmetry. It means that what we perceive as solid, immovable matter is at its core a frozen form of energy, potential waiting to be released. And that same equation also explains why light, which has no rest mass, must always move at the ultimate speed. Because it has energy but no mass, it doesn't need to accelerate at all. It simply is motion, traveling eternally at the universe's built-in limit. So while time dilation and length contraction show us how motion reshapes experience, the increase of mass with velocity shows us why that reshaping can never go too far. Together, they form a trinity of cosmic checks and balances. Time slows, space contracts, and mass grows, all conspiring to protect the speed of light as the one unbreakable constant.
This, then, is the great irony of the universe. The harder we try to move faster, the more the universe resists. The faster we go, the heavier we become. The more energy we pour in, the less it matters. Light alone, weightless and timeless, is free to dance across space-time at the ultimate speed. Never aging, never slowing, never stopping. But why can light do that? Why is it exempt from this rule that binds everything else? The answer lies in its nature, not as a massive object, but as a massless particle, a ripple in space-time itself. And in that lies the next piece of our journey through the universe's greatest limit. Light's special status in the universe, its ability to travel at the ultimate speed limit, comes down to a single defining feature. Photons have no rest mass. Unlike matter, which resists acceleration because of its inertia, photons are weightless quanta of pure energy. They do not experience time, do not possess a state of rest, and can never slow down or speed up. In fact, to stand still is an impossible concept for light. It exists only as motion. To understand why, let's step back and consider what mass really means in Einstein's universe. Mass is what anchors an object in space-time. It's the measure of how strongly an object resists changes in its state of motion. The more mass something has, the more energy it takes to move or accelerate it. But for something that has no rest mass, that anchor simply doesn't exist. There's no inertia to overcome, no resistance to motion. And because the universe's structure enforces that all energy must travel through space-time in some way, a massless particle can't just sit still. It must move at the one speed available to it, the speed of light, c. That speed isn't arbitrary. It's the ultimate conversion rate between space and time, the constant built into the geometry of the cosmos itself. Light doesn't merely choose to travel at that speed. The laws of nature require it. A photon born at that velocity has no option to go slower or faster. It is forever racing through space-time along the only trajectory that's physically possible for something with zero rest mass. If we imagine trying to slow a photon down, even slightly, we'd immediately run into contradiction. To move slower than light, it would need to have a non-zero rest mass, but that would mean it could exist in a state of rest, and photons simply can't. On the flip side, if the photon could somehow move faster than light, it would break the very geometry of space-time where cause and effect are defined. It would leap outside the fabric of the possible, defying causality itself. So the photon lives precisely at the edge, moving through space at the cosmic limit and not at all through time. This is why, from light's perspective, time does not pass. A photon emitted from a star billions of light years away, and one absorbed by your eye right now, experience no interval between those two moments. To us, that photon's journey took eons, crossing vast stretches of intergalactic space. But from the photon's point of view, if we can even use that phrase, both events are simultaneous. Its birth and death, its departure and arrival, are the same moment. Light doesn't experience distance or duration the way massive objects do. It simply is. You could say that light exists on the boundary of space-time, the razor-thin edge separating the possible from the impossible. Everything with mass must travel within that boundary, slower than light, because mass ties you to time.
Light, massless and free, moves along the edge itself, neither stepping into time nor falling behind it. That's what we can think of the speed of light not as the velocity of a particular thing, but as a property of space-time itself. It's how fast reality can communicate with itself, how quickly cause can lead to effect. There's something beautifully consistent about this. Light defines the universe's most fundamental measurements, not because of what it is, but because of what it represents. Every interaction, every exchange of information, every flicker of causality happens at or below that same limit. It's as if light is the cosmic messenger carrying the laws of physics across the fabric of existence, always at the same pace, never faltering, never changing. This also explains why all massless particles, not just photons, share this property. If gravitons, the hypothetical carriers of gravity, exist, they too would travel at the speed of light for the same reason. With no rest mass, they have no way to move slower. The same is true for gluons, which carry the strong nuclear force inside atoms, although their motion is confined by other forces within matter. So light, in a sense, is both a participant and a referee in the universe's grand game. It's the medium through which all energy, information, and causality flow, and it defines the rules by which they must play. Everything else, every particle, planet, and person, moves through space-time at less than light speed because it must. Light itself exists at the edge of that constraint, the pure embodiment of motion. But there's another, deeper reason the speed of light is the universe's limit. It's not just about how fast things can move. It's about what can influence what. Exceeding that speed would mean sending information, or cause, faster than reality itself can process it. And if that were possible, it would tear apart one of the most sacred principles of the cosmos, causality.
Causality is one of the deepest and most sacred principles in the universe. The idea that causes always precede their effects. A match must strike before it ignites. A word must be spoken before it's heard. This simple ordering of events underlies not just physics, but logic, experience, and existence itself. Without causality, reality would dissolve into paradox. Yet, as Einstein's theory revealed, if anything could move faster than light, causality would shatter. The chain of cause and effect would twist back on itself, and the universe would lose its ability to make sense. To understand why, we have to look at how time behaves under relativity. When two observers move relative to each other, they don't agree on the timing of distant events. What one observer sees as now might be the past or future for another. At ordinary speeds, this disagreement is tiny and unnoticeable. But as you approach the speed of light, that difference becomes enormous. If you could somehow send information faster than light, you could exploit those differences to send messages into the past. Imagine a thought experiment. You're standing on Earth and your friend is on a planet several light years away. You both have extremely fast transmitters. One's capable of sending signals faster than light. You send your friend a message, and because your signal breaks the universal speed limit, it reaches them almost instantly. Now suppose your friend replies just as fast, sending a return signal that also travels faster than light. But because of the way time and space mix under relativity, that reply could actually reach you before you set your original message. You've now created a paradox. You received the reply before you've written the message. Cause and effect have flipped. You could, in theory, use that information to change your decision, to not send the message at all. But then, if you never sent the message, your friend could never have replied. The entire sequence collapses into contradiction. This is known as a causal loop, or sometimes the tachyonic paradox, named after hypothetical faster-than-light particles called tachyons. It's not just communication that breaks down, reality itself does. If signals, particles, or objects could move faster than light, you could construct scenarios where an effect triggers its own cause. Imagine a gun that fires a bullet faster than light, hitting a target before the trigger is pulled. The bullet's impact could, theoretically, prevent the trigger from being pulled in the first place, erasing the very event that created it. It's the same logical impossibility as the famous grandfather paradox from time travel stories. If you went back in time and prevented your grandparents from meeting, you would never be born. But if you were never born, who went back to stop them?
Einstein's equations, when taken seriously, show that faster-than-light motion would open precisely these kinds of causal violations. The fabric of space-time doesn't just discourage such behavior, it makes it mathematically inconsistent. The geometry of relativity defines what events can influence one another through what's called the light cone. Inside that cone are all events that can be connected by signals moving at or below the speed of light, events that can cause or be caused. Anything outside the cone lies beyond reach. No influence, no message, no causal link can cross that boundary. The speed of light, then, isn't merely a physical limit, it's the boundary of causality itself. It's what keeps the universe from devolving into paradox and chaos. Exceeding it would be like stepping outside the logic of reality, where time and sequence lose meaning. Let's push this thought experiment one step further. Suppose some advanced civilization managed to develop a ship that could travel faster than light, perhaps using some exotic technology that bends space itself. If such a ship sent a distress signal home while moving at those speeds, observers in different reference frames could disagree on when that message was sent and when it was received. For some, it might look like the ship called for help after an accident. For others, the call might appear to have come before the accident happened. In certain frames, the message could even appear to have been received before it was transmitted. You've now created a paradox. You receive the reply before you've written the message. Cause and effect have flipped. You could, in theory, use that information to change your decision, to not send the message at all. But then, if you never sent the message, your friend could never have replied. The entire sequence collapses into contradiction. This is not just science fiction confusion, it's baked into the mathematics of relativity. Once you allow faster-than-light travel or communication, there is no single, consistent ordering of events that all observers can agree on. The concept of a universal timeline breaks down completely. Each observer's sense of before and after becomes subjective. And since the universe can't sustain contradictory histories, relativity forbids such motion outright. In a very real sense, the speed of light is what keeps the universe logical. It draws a clean, unbreakable line between what can happen and what cannot. Everything that happens, from a particle decay to the movement of galaxies, must respect this boundary. If it didn't, the cosmos would be littered with paradoxes, events that both happened and didn't, effects without causes, causes without origins. This is why physicists sometimes say that the speed of light isn't about light at all. It's about information. Nothing, not even a whisper of data, can move faster than light because information itself defines the unfolding of cause and effect. Allowing information to move faster than light would mean allowing the future to rewrite the past, a concept that collapses not just physics, but logic itself. Thus, the speed of light is the thread that stitches the fabric of reality together. It's the universal rhythm that ensures the sequence of events makes sense no matter who observes them or where they are. And this boundary, this invisible wall defined by the speed of light, gives rise to one of the most elegant structures in modern physics: the light cone. The light cone is the map of causality itself, showing what parts of spacetime can influence you, what parts you can influence, and what lies forever beyond your reach. In the grand architecture of Einstein's universe, nothing illustrates the logic of spacetime more clearly or beautifully than the light cone. It's not just a diagram physicists draw on paper, it's a profound representation of how reality itself is structured, how cause and effect are organized, and how the speed of light determines what can influence what. Every event that has ever happened, or will ever happen, exists within this geometrical framework. To imagine a light cone, start with a single event, a point in spacetime. It could be anything: a flash of lightning, the spark of a match, the moment you snap your fingers. That event has a position in space and a moment in time, and from it, light radiates outward in all directions at the same constant speed. As time passes, that light spreads farther and farther away, tracing an expanding sphere of influence through the universe. If you could plot that expansion on a space-time diagram, with time going upward and space extending horizontally, that sphere would appear as a cone, widening as light travels outward. That cone represents all the points in space-time that can possibly be affected by the original event, the region into which light or any signal traveling slower than light could reach. We call that region the future light cone. Everything inside it lies in the potential future of that event. Everything outside it lies forever beyond its reach. Now imagine the reverse. Instead of light moving outward, think of light converging inward toward that same point. That defines the past light cone, the set of all events that could have possibly influenced or caused the event at the tip. Every photon that ever could have reached that point, every signal that could have arrived there, must have originated somewhere inside that cone.
Together, the past and future light cones form a kind of hourglass centered on any given event. The lower cone represents the past, everything that could have led up to this moment. The upper cone represents the future, everything that can still be affected by it. And everything outside those cones is the elsewhere region, parts of space-time that are neither in causal contact with the event nor ever can be. No information, no force, no influence can cross from those regions into the cones without breaking the cosmic speed limit. This simple geometric structure, two cones touching at a point, encodes the very essence of relativity. It defines causality. It tells us that what we call the present isn't the universal slice of time shared across the cosmos, but a local experience bounded by the speed of light. Your now includes only what's within your light cone, what you can currently influence or perceive. Everything beyond it is, in a sense, not yet real to you. For instance, the light from a distant galaxy a billion light years away is only reaching us today. That means our present moment includes the galaxy as it was a billion years ago, not as it is now. The galaxy's current state lies outside our present light cone, part of a future we cannot yet observe or affect. Similarly, there are countless galaxies so far away that their light will never reach us, because the universe's expansion is carrying them beyond our causal horizon. They exist, but they are forever sealed off, outside both our past and future light cones. In this sense, the light cone defines what we mean by the observable universe. It's not just a measure of distance, it's a measure of causality, the boundary of what can ever have a physical connection with us. Anything outside it is causally disconnected, unreachable by any signal, forever beyond influence or knowledge. The light cone concept also provides a simple, elegant way to visualize why faster-than-light travel or communication would wreck causality. If something could move faster than light, its path would jump outside the light cone, slipping into regions of space-time that are supposed to be causally unreachable. Depending on the observer's frame of reference, that event could even appear to move backward in time, making cause and effect interchangeable. That's why in relativity, the light cone isn't just a helpful diagram, it's the law of order for the entire universe. It tells us what can cause what can influence what, and what lies beyond all possible influence. Every particle, every planet, every moment of your life traces its own world line through space-time, threading upward through its series of light cones. Your birth, your experiences, your future, all lie along that line, defined by what your light cone allows you to touch. When you send a signal, you are shaping the future within your cone. When you look at the stars, you are peering into your past light cone, reading the history of the cosmos written in light. The most extraordinary realization is that this structure is universal. Every point in space-time, every atom, every event, every burst of light has its own light cone, its own causal horizon. And together, these overlapping cones form the intricate web of connections that make up the universe itself. It's like a vast cosmic mosaic where every piece is bound by the same simple rule: no influence travels faster than light. This geometry doesn't just organize the physical world, it organizes reality itself. The light cone is the skeleton of space-time, the scaffolding upon which time unfolds and events connect. It ensures that the universe has a coherent narrative where every cause leads cleanly to its effect. But there's a deeper insight hidden in this geometry. The speed of light isn't really about light at all. It's not that photons are uniquely special. It's that they happen to travel at the maximum speed that space-time allows. What we call the speed of light is really the speed of causality, the rate at which information, energy, or influence can propagate through the universe.
It's the fastest that cause can lead to effect. Every event, every signal, every exchange of information is bound by this same ultimate pace because this is how reality preserves its logical structure. To understand why this distinction matters, imagine a universe without light. Even if no photons existed, the value of c would still define the limits of motion and communication. Gravitational waves, ripples in space-time itself, also travel at c. If the hypothetical particles that carry gravity, called gravitons, exist, they too would move at c. Even the nuclear force carriers, like gluons, when free of confinement, would follow the same law. In short, c is the speed limit for information, not the speed of any particular phenomenon. When physicists talk about c, they often don't even call it the speed of light. They simply refer to it as the fundamental constant of spacetime. It's the conversion rate between space and time, the factor that ties distance and duration together. In a sense, it's the slope of the universe's fabric, dictating how far you move in space for every tick of time if you're moving at the ultimate possible pace. Light, being massless, just happens to live on that slope perfectly. It has no rest frame, no perspective of its own because it's always moving at c. But the same constant governs the upper bound of every other form of motion or influence. The gravitational tug of one star on another, the communication between particles, even the transmission of information in a computer chip, all of it is constrained by the same cosmic speed limit. This also means that c is woven into the very definitions of space and time themselves. When Einstein reimagined the universe as a single space-time fabric, c emerged as the fundamental constant that translates between spatial distances and temporal intervals. It's why physicists can measure distances in seconds or time in meters, because in the universe's equations, space and time are different facets of one entity, connected by c. Think of it like this. If space and time were currencies, c would be the exchange rate that allows you to convert one into the other. It tells you how many meters of space correspond to 1 second of time, or how much duration is equivalent to a given stretch of distance. Without that exchange rate, the entire economy of the universe, its geometry, motion, and causality would collapse. So when we talk about the speed of light, we're really talking about the speed of reality. It's how fast a signal can cross space-time to link one event to another, ensuring that the order of cause and effect remains consistent everywhere. That's why c shows up not only in electromagnetism, but in relativity, quantum field theory, and the very equations describing energy and mass. It's the universal translator between everything that happens. Even the concept of information, the intangible, abstract essence of knowledge and causation, is tied to this constant. You can't send information faster than c, because doing so would break the chain of logic connecting events. The universe protects its own consistency by making c the ultimate ceiling for everything that exists or can exist. In this sense, light is less the reason for the cosmic speed limit than the messenger of it. Photons travel at c not because light has special privileges, but because it perfectly embodies what happens when mass and inertia disappear. It's nature's way of expressing pure motion, the clean limit of energy unburdened by matter. This reframing also deepens our philosophical understanding of the cosmos. The speed of light isn't a limitation to be overcome. It's a definition of reality itself. It's what keeps the universe logical, coherent, and connected. Without it, causality would unravel, the fabric of space-time would lose structure, and the distinction between past and future would vanish. So the next time we call it the speed of light, it's worth remembering that we're really speaking of something far grander, the speed of reality. Light is simply the most visible expression of that law, the constant reminder that the universe moves according to an elegant and unbreakable rhythm that binds space, time, and causality into one seamless whole. And light isn't alone in this race along the cosmic boundary. Other massless entities, theoretical and real, also inhabit this limit, proving that c governs not just illumination, but the motion of all fundamental interactions.
While light is the most familiar traveler at the universe's ultimate speed, it's far from alone in principle. In the subatomic world, the deep, invisible realm where the rules of reality are written, other particles also inhabit this same cosmic boundary. These are the massless particles, the pure carriers of nature's fundamental forces. Whether we're talking about photons, gluons, or the still hypothetical gravitons, they all share one defining trait. They have zero rest mass, and therefore they must travel at the speed of light, c, not by choice, but by necessity. To see why, we can look at how nature treats particles with and without mass. A massive particle, like an electron or a proton, can exist at rest. It can sit still, carry energy by virtue of its mass, and move through time even when not moving through space. But for a massless particle, the situation is entirely different. Because it has no rest mass, it cannot exist in a stationary state. If it ever stopped moving, it would lose all energy, cease to exist as a particle, and vanish into nothing. For something massless, motion at light speed isn't just what it does, it's what it is. The most familiar example, of course, is the photon, the particle of light. It is both wave and particle, both energy and momentum without mass. But photons are only one kind of massless messenger. In the framework of modern physics, force carriers, the mediators of the fundamental interactions, are often massless as well, at least in theory or under certain conditions. Take the gluon, for example, the particle that carries the strong nuclear force, the force that binds quarks together inside atomic nuclei. Gluons are massless in the equations of quantum chromodynamics, the theory that describes the strong force. They move at light speed, just like photons, but there's a catch. Gluons are never seen traveling freely through space. They are permanently confined within the interiors of atomic nuclei, trapped by the very force they carry. This property, known as color confinement, means gluons are like lightning bolts that never strike outside the storm. They move at sea within their own microscopic prison, zipping between quarks at unimaginable speeds, binding the cores of atoms together with an energy so intense that it accounts for nearly all the mass of the visible universe. Then there's the graviton, the hypothetical particle thought to mediate the force of gravity. In Einstein's general relativity, gravity isn't technically a force, but the curvature of space-time caused by mass and energy. Yet in quantum field theory, every force has a carrier particle. In gravity's would be the graviton. If it exists, it would have to be massless. Why? Because gravity operates over infinite distances, and only a massless particle can mediate an infinite range interaction. If the graviton had mass, gravity would weaken rapidly with distance, and the large-scale structure of the universe, galaxies, clusters, cosmic webs, would not exist as it does. So, by definition, the graviton would travel at exactly the speed of light, carrying changes in gravitational fields across the universe at the same pace as photons carry light. In fact, we've already seen indirect proof of this through the detection of gravitational waves, ripples in space-time caused by massive events like colliding black holes. These waves, first directly observed in 2015 by the LIGO experiment, move through space at precisely the same speed as light, to within the limits of experimental accuracy. If gravitons are the quantum particles underlying those waves, they too must move at c, confirming that this speed is not just the domain of light, but the limit for all massless excitations of space-time itself. Even more abstractly, in the early moments of the Big Bang, the universe was filled with massless energy. Before the Higgs field switched on and gave particles mass, everything, electrons, quarks, neutrinos, and all the primordial radiation moved at the speed of light. It was only after the universe cooled and the Higgs mechanism took effect that most particles slowed down, gaining mass and stepping off that cosmic racetrack. In that sense, the universe itself was once a sea of light-speed motion, with no distinction between massless and massive states. This distinction between massless and massive particles defines the very structure of existence. Massless particles travel through space but do not experience time. Massive particles travel through time but can never reach the limit of space. Between those two extremes lies everything that exists, every atom, every planet, every conscious being. The massless realm defines the boundaries of space-time, while the massive realm defines the content within it. Light, gluons, and hypothetical gravitons aren't just fast, they are the framework through which the universe holds itself together. They carry the forces that shape everything. Light communicates electromagnetic interactions, gluons hold nuclei together, and gravitons, if real, would weave the curvature of space-time itself. And each of them travels at the same unyielding speed,
the same constant c, as if the universe itself uses this velocity as its own heartbeat. So when we think of the speed of light, we should picture it not as a special feature of illumination, but as the universal tempo of energy without mass. Anything with rest mass must forever move beneath that limit, bound to the flow of time. Anything without mass must forever move at that limit, bound to the geometry of light-speed existence. There is no in-between. And this cosmic divide between the massive and the massless has profound implications, not just for the laws of motion, but for our dreams of exploration. Because for all our technological imagination, for all our stories of warp drives and faster-than-light travel, the truth remains: this boundary is absolute. For us, travelers made of mass and matter, space will always be a vast and patient ocean. And even moving close to light speed, the stars remain unimaginably far. Picking up from the massless messengers that define the cosmic speed limit, let's turn to a practical question everyone thinks about. What does that universal limit mean for travel between the stars? Even if we could build a starship that approached the speed of light, the distances are enormous. Proxima Centauri, our nearest neighbor star, is about 4.24 light-years away. That is, light takes just over 4 years to travel from there to here. If a spacecraft somehow managed to cruise at 10th% of light speed, the trip would take a little over 40 years as seen from Earth. Pushed to half the speed of light, the Earth frame travel time drops to under 9 years. Go to 90% of light speed, the journey would take roughly 4 3/4 years by Earth clocks. At 99% of light speed, Earth observers would measure about 4.28 years for the trip.
Those are Earth frame times. From the perspective of people aboard a near-light-speed ship, relativistic effects change the experience. Time aboard the vessel runs more slowly compared with time on Earth. For example, at 90% of light speed, the ship's onboard clocks would accumulate a couple of years while Earth ages nearly 5. At 99% of light speed, the crew's subjective trip could be only a few months while more than 4 years pass back home. In other words, going very fast lets you outpace Earth time to some degree, but it does not let you beat causality, nor does it make the distances trivial. The practical barriers, however, are enormous, and not just about subjective time. The main showstoppers are energy and propulsion. Accelerating a massive ship to even a significant fraction of light speed requires stupendous energy. As speed rises, each additional fraction of velocity costs more and more energy. Current chemical rockets are insignificantly weak compared to what would be needed. Even speculative concepts like fusion or antimatter propulsion face massive fuel mass, storage, and engineering challenges. Acceleration and human limits. To reach near light speeds within a human lifespan, you need sustained high acceleration, which imposes severe physiological stresses and structural strains. Alternatively, extremely low acceleration over decades requires reliable systems and supply for generations. Interstellar medium and shielding. Space is not perfectly empty. Even sparse hydrogen atoms and dust grains at relativistic speeds become dangerous projectiles. Tiny particles hitting a ship at a large fraction of light speed carry enormous kinetic energy and can erode or penetrate shielding, generate crippling radiation, or produce deadly secondary showers. Effective shielding adds weight, which increases energy needs, a vicious cycle. Deceleration and rendezvous. Reaching a star is only half the mission. Slowing down to orbit or land requires comparable energy and planning. A one-way high-speed flyby that cannot decelerate has limited scientific and colonization value. Communication lag and mission control. Even at near light speed, two-way communication with Earth suffers the light travel delay. And because Earth and the ship age differently, mission planning and social continuity become complex. Science fiction's common shortcuts, instantaneous jump drives, hyperspace tunnels, and simple warp bubbles that let you point and go faster than light all face two kinds of fundamental resistance. One is physical. As discussed earlier, exceeding the speed of light for objects with mass would require violating the structure of spacetime or supplying infinite energy. The other is logical.
faster-than-light signaling tends to open causal paradoxes, messages into the past, which would unpick the universe's logical order, unless some new physics guardrails are discovered. There are speculative loopholes that try to get around these constraints without literally accelerating a ship through space faster than light. Ideas include bending or rearranging space-time locally so that a ship rides a contracted bubble of space, or traverses a shortcut through a heavily curved region, a wormhole. In principle, these approaches don't accelerate the ship past light speed locally. They manipulate the geometry of space itself, but they come with their own forbidding problems. They seem to demand exotic forms of energy, negative energy density, astronomical energy budgets, and they raise thorny questions about stability, horizons, and causality. None of these ideas currently sits on a firm experimental or engineering foundation. So the sober takeaway: with known physics, interstellar travel at anything approaching light speed is theoretically possible, but practically gargantuan in cost, engineering difficulty, and risk. You can shorten journey experience through relativistic time dilation, but you cannot cheat the energy, shielding, and causality realities. That's why the nearest stars still feel extremely far away, in practical terms, and why so much of realistic thinking about humanity's future among the stars focuses on generational ships, propulsion breakthroughs, or ways to minimize the need to accelerate large masses to relativistic speeds. There is one fascinating and often misunderstood exception to the universal speed limit, an effect that seems, at first glance, to show particles moving faster than light. You may have seen it without realizing it, an eerie blue glow radiating from the heart of a nuclear reactor, rippling through the cooling water like ghostly lightning. That glow is known as Cherenkov radiation, and while it's a stunning demonstration of high-energy physics, it does not break the laws of relativity. Instead, it reveals something subtle and beautiful about how light behaves when it passes through matter. Here's what's actually happening. The cosmic speed limit, the speed of light, c, applies only to light in a vacuum, where nothing slows it down. But when light travels through a medium, like water, glass, or air, it interacts with the atoms and molecules in that material. Each photon is absorbed and re-emitted countless times, a process that effectively slows down the propagation of light's wavefront. In water, for example, light moves at about 3/4 of its vacuum speed. In glass, it slows even more. Meanwhile, charged particles, such as electrons, can pass through those same materials, almost unaffected, especially if they are highly energetic. Inside a nuclear reactor, radioactive decay launches electrons that are moving at a large fraction of c, sometimes so fast that they actually outrun light as it moves through the medium. Think of this like a sonic boom, but for light. When a jet flies faster than the speed of sound in air, it outruns the sound waves it produces, creating a sharp cone of compressed pressure that we hear as thunderous boom. Similarly, when an electron moves through water faster than light can propagate in that medium, it creates a cone of electromagnetic shockwaves, a cascade of photons emitted at a specific angle. This electromagnetic boom manifests as that deep electric blue glow we call Cherenkov radiation. It's worth emphasizing that these electrons aren't actually breaking the cosmic speed limit. They're moving faster than light in that particular medium, not faster than light in vacuum. Even at their most energetic, they're still below the universal speed limit. The photons they emit, the shockwaves of light, are the result of them disturbing the local electromagnetic field faster than the slowed-down light waves can keep up. To visualize it, imagine standing in shallow water at the edge of a pond. You start walking quickly, faster than the ripples can spread through the water surface. Those ripples overlap and pile up into a distinct V-shaped wake trailing behind you. That's what the electron is doing, leaving behind a light wake instead of a water wake. And because light's speed depends on the refractive index of the medium, this phenomenon can happen in water, glass, or even transparent crystals, anywhere light is slowed down enough for a charged particle to overtake it. The blue color is no coincidence either. The emitted radiation tends to be stronger at shorter wavelengths, and blue light has one of the shortest visible wavelengths. So the resulting glow, often seen in nuclear reactors or particle detectors, carries that distinctive blue signature, the light equivalent of a sonic boom frozen into the visual spectrum. Cherenkov radiation has turned out to be far more than a curiosity. It's an incredibly useful tool in experimental physics. In particle detectors, scientists use the angle and intensity of Cherenkov light to determine the speed and energy of fast-moving particles. It's also used in medical and astrophysical contexts. In neutrino detectors, for example, where massive tanks of water or ice buried underground wait for rare flashes of Cherenkov light from elusive cosmic particles. But most importantly, Cherenkov radiation reminds us that faster than light depends on context. The universal constant c is the true speed of light in vacuum, the speed at which information and causality propagate through space-time itself. But when light passes through matter, its effective speed drops, and other particles can appear to surpass it locally without violating the deeper rules of relativity.
In other words, Cherenkov radiation is the universe's way of letting us see where relativity bends but does not break. The blue glow is a visual signature of particles dancing right up against the edge of the possible, moving faster than light's slowed-down pace in matter, yet never daring to cross the true cosmic line drawn by c. So even though Cherenkov radiation might look like light's speed limit is being broken, it's actually a brilliant demonstration of how steadfast that limit really is. The cosmic rule holds. It's only light in the medium that slows, and energetic particles that take advantage of that momentary lag to leave a trail of blue fire in their wake. It's a beautiful paradox resolved by deeper understanding, one that reaffirms that nothing, anywhere, ever outruns light in a vacuum. Still, there's one more mysterious phenomenon in physics that seems to challenge this boundary in its own way: quantum entanglement. It appears to allow instantaneous connections between distant particles, as if information leaps across the cosmos faster than light. But as we'll see, even here, nature's laws find a way to preserve causality. Cherenkov's blue wake fades, and suddenly we confront an even stranger-looking phenomenon: quantum entanglement, the spooky connection that seems to let particles know about each other instantly across vast distances. At first glance, entanglement seems to flirt with breaking the cosmic speed limit. Measure one particle here, and its partner's state appears fixed immediately over there. But beneath the drama, the laws of physics keep causality intact. Entanglement means two or more quantum systems share a single joint description, so that measurements on one are correlated with measurements on the other. If you prepare a pair in a perfectly correlated state and send them far apart, an observer measuring particle A will get a random outcome. An observer measuring particle B will also get random outcomes. Only after the two observers compare results do the perfect correlations become apparent. Crucially, nothing you do to particle A can force a chosen controllable outcome at B. The local statistics at B don't change when A is measured. From B's perspective alone, the results look random regardless of what happens to A. That inability to control outcomes is the key to why entanglement cannot be used for faster-than-light messaging. To send a message, you must be able to encode and decode information intentionally. Entanglement gives correlations, not controllable signals. Any attempt to use measurements, state changes, or even clever quantum tricks runs headlong into the no-signaling theorem. No local operation on one subsystem can change the marginal probability distribution of outcomes seen at the other subsystem. You'd still need a classical communication channel limited by C to compare notes and extract the message. Teleportation and entanglement swapping illustrate the same point. Quantum teleportation can transfer the state of a particle from A to B, but only after a classical message telling B how to finish the protocol arrives. Without that classical step, the teleported state is inaccessible. So teleportation doesn't bypass relativity. It marries quantum correlations with classical channels that obey the light speed limit. Physically, another way to think about it: entanglement encodes joint information spread across systems, not a signal sitting in one place waiting to be shuttled. When a measurement occurs, what collapses is an update of our description of the joint system, an informational change, not a transferable packet of cause that outruns light.
Different interpretations of quantum mechanics, collapse, many worlds, relational views, describe this process differently, but all preserve the empirical fact no faster-than-light communication. Experimental tests of Bell inequalities and long-distance entanglement have repeatedly shown strong, non-local correlations, while also confirming that those correlations cannot be exploited for superluminal signaling. Even ambitious demonstrations that entangle particles across satellites and ground stations still require classical channels to verify correlations, and those channels know no faster than light. So entanglement is startling, but not law-breaking. It stretches our intuitions about separability and locality, yet it doesn't let information outrun causality. It highlights that instantaneous in quantum language refers to correlations, not to usable controllable signals. The cosmic speed limit stands. One of the most mind-bending realizations in modern cosmology is that while nothing can move through space faster than light, space itself can expand faster than light, and does. This isn't poetic exaggeration. It's a literal description of how our universe behaves on the largest scales. When we peer deep into the cosmos, we see galaxies receding from us at astonishing speeds, some apparently faster than light itself. Yet this superluminal expansion doesn't break Einstein's cosmic speed limit. The key lies in understanding the profound distinction between motion through space and the stretching of space itself. To visualize this, imagine space not as a fixed stage on which galaxies move, but as an elastic fabric that can stretch, twist, and warp. This is the very picture introduced by general relativity. Space-time isn't static, but dynamic, responding to energy and mass. Galaxies on cosmic scales aren't racing like rockets through this fabric. They're more like dots painted on the surface of a balloon that's being inflated. As the balloon expands, every dot moves away from every other dot, not because they're sliding across the surface, because the surface itself is stretching. The farther apart the dots, the faster they separate because there's more balloon between them to expand.
In our universe, this stretching of space means that the recession velocity of distant galaxies can exceed the speed of light without violating relativity. Why? Because relativity's speed limit applies locally, to motion through space measured in a local frame of reference, not to the rate at which the metric of space-time itself changes over vast distances. Within any local region of space, say within a galaxy or a solar system, light remains supreme. But over billions of light years, the cumulative stretching of space can make distant regions appear to move away faster than light can travel. This cosmic expansion isn't a new or recent phenomenon. It's been happening since the universe's earliest moments. But in the very beginning, during the brief, extraordinary era known as cosmic inflation, it happened on a scale and at a speed almost beyond comprehension. In the first fraction of a second after the Big Bang, space itself expanded exponentially, doubling in size again and again in less than a heartbeat. During this inflationary epoch, regions of the universe that were once microscopically close were driven apart faster than any light signal could bridge the gap. Entire regions became permanently causally disconnected, forming the vast, smooth cosmos we inhabit today. Even now, the universe's expansion continues, though at a gentler pace. Observations of distant supernovae and the cosmic microwave background have revealed that this expansion is accelerating, driven by a mysterious force we call dark energy. Because of this acceleration, some galaxies are not just receding from us faster than light, they are doing so at an ever-increasing rate. Their light, emitted today, will never reach us, no matter how long we wait. They are crossing what cosmologists call the cosmic event horizon, leaving our observable universe forever. It's a humbling thought. The visible cosmos is not the whole universe, but merely the part we can still exchange light with. Beyond that boundary, billions, perhaps trillions of galaxies are receding into darkness, their signals eternally out of reach, not because they're breaking the rules of physics, but because the rules themselves allow space-time to stretch. Relativity forbids objects from overtaking light within space, but it places no limit on how fast space itself can expand. This distinction between moving through space and the movement of space is subtle but fundamental. You can think of light as the fastest runner on the cosmic track, and space as the track itself being stretched by unseen hands. The runner always moves at the same speed relative to the track, but the distance between points on the track can grow faster than any runner could ever cover. And yet,
Even in this vast and expanding cosmos, relativity holds firm. Locally, everywhere, the laws of physics remain the same. An observer in a distant galaxy sees their own surroundings behaving exactly as we do here. Light still moves at sea, time still flows according to the same equations, and the same physical laws govern their stars and atoms. The cosmic expansion doesn't tear local systems apart, because gravity and other forces keep them bound. The atoms in your body, the Earth's orbit around the Sun, the Milky Way's spiral arms all remain stable, unaffected by the grand stretching of the universe at large. Cosmic expansion therefore doesn't violate relativity. It's one of its most beautiful predictions. General relativity doesn't just describe how gravity pulls, it also allows space-time itself to evolve dynamically. The expanding universe is simply one grand solution to Einstein's equations, a living, breathing cosmos where distances grow, horizons shift, and yet the ultimate speed of light, the guardian of causality, remains untouched. But physicists, ever restless, have wondered if the expansion of space could somehow be used, if there might be ways to ride or manipulate space-time itself to reach distant stars without technically breaking the speed limit. From that curiosity comes the realm of speculative physics, warp drives, wormholes, and other theoretical loopholes that attempt to bend space rather than outrun light. Concepts that sound like science fiction, but are grounded, at least mathematically, in the same equations Einstein gave us. The idea of space itself expanding faster than light naturally tempts the imagination. If the universe can stretch faster than light, could we somehow use that property to travel the stars? Could we bend space around us, compressing it in front and stretching it behind to cross impossible distances without technically moving faster than light? This is where speculative physics enters the conversation, blurring the line between deep theoretical possibility and science fiction wonder. One of the most famous proposals comes from the early 1990s, when the Mexican physicist Miguel Alcubierre proposed a solution to Einstein's general relativity equations that appeared to allow faster-than-light travel, not by moving through space faster than light, but by moving space itself. The concept, now known as the Alcubierre drive, imagines a spacecraft enclosed in a warp bubble of space-time. Inside that bubble, the craft would remain stationary relative to its local space, while the region of space-time behind it expands and the region in front contracts. From the outside, the bubble and everything within it could appear to travel faster than light relative to distant observers, but no part of the ship inside would ever locally exceed light speed. This distinction is subtle yet profound, and it's what makes the Alcubierre drive so fascinating. It doesn't break relativity, it exploits it. Within the local bubble, the ship isn't accelerating at all. There are no g-forces crushing the passengers, no rockets burning, no violations of Einstein's equations. Instead, the craft is surfing a wave of space-time, riding the curvature of the universe itself like a cosmic surfer. Theoretically, the ship could cross light years in days or even hours depending on how the bubble's geometry is shaped. But as elegant as this idea sounds, it comes with enormous and likely unsurmountable challenges. The first and most fundamental problem is energy. To bend space-time in the way Alcubierre described would require mind-boggling amounts of it, far exceeding anything humanity could ever hope to generate. Early estimates suggested that to move even a modest spacecraft, you would need more energy than is contained in the entire observable universe. Later refinements brought that number down, but it's still impossibly huge. Even more problematic is the type of energy required. The Alcubierre drive demands negative energy density, a condition that doesn't exist in any known classical matter. Negative energy isn't just less energy, it's energy that warps space-time in the opposite direction of normal matter, effectively creating regions of repulsive gravity. While quantum physics allows fleeting appearances of negative energy in phenomenon like the Casimir effect, where vacuum fluctuations between two close metal plates produce a tiny attractive force, these effects are extraordinarily small and unstable. Nothing like the sustained, controllable negative energy needed to power a warp bubble has ever been observed, and it's not clear that such matter could exist in any stable form.
There are also deeper theoretical issues. If a warp bubble could form, it might create causality paradoxes similar to those seen in faster-than-light travel. The edges of the bubble, the warp front, could act as horizons, regions beyond which signals can't escape or enter, much like the event horizon of a black hole.
That means anyone inside the bubble couldn't control it once it's created, because no signal could travel from the ship to the bubble's edge faster than the bubble itself is moving. In other words, you could start a warp bubble, but you might not be able to stop or steer it. Another problem lies in the sheer instability of such a configuration. Even if the required energy somehow existed, quantum field effects at the bubble's boundaries could become catastrophic. Tiny fluctuations could amplify uncontrollably, possibly destroying the bubble or releasing destructive bursts of radiation. In simulations, the bubble edges tend to collapse or pinch off, a mathematical hint that the structure might not be physically realizable. A similar set of challenges plagues the idea of wormholes, hypothetical tunnels connecting distant regions of spacetime. General relativity allows such solutions mathematically, in which space curves so extremely that it folds back on itself, creating a shortcut from one region to another. A wormhole could, in principle, connect two distant galaxies or even two different times. But to keep the wormhole throat open against gravitational collapse, you again need exotic matter with negative energy density, the same elusive ingredient demanded by the Alcubierre drive. Without it, the wormhole would pinch shut faster than any traveler could enter. Even if such exotic matter existed, traversable wormholes introduce their own paradoxes. Depending on how they're arranged, they could allow paths through spacetime that effectively lead backward in time, violating causality. Nature seems to abhor such possibilities. Many physicists suspect that a yet unknown aspect of quantum gravity, the theory uniting quantum mechanics and general relativity, would ultimately forbid them. Stephen Hawking famously referred to this as the chronology protection conjecture, the idea that the laws of physics prevent time travel to preserve causality. Still, these concepts are valuable, not because they offer engineering blueprints, but because they stretch our imagination and force us to probe the boundaries of Einstein's equations. They remind us that space-time is not static or rigid. It's a flexible fabric that, under the right conditions, could in principle be shaped. Whether humanity will ever find a way to manipulate that fabric remains unknown, but the theoretical exercises have already enriched our understanding of the cosmos. For now, the dream of faster-than-light travel remains confined to the realm of mathematics and imagination. The Alcubierre drive and wormholes may never carry a real spacecraft between the stars, but they continue to illuminate the deeper truth that relativity revealed. Space and time are malleable, but they are not lawless. The universe has structure, boundaries, and symmetries that preserve causality, the thread that keeps reality coherent. And in that coherence lies a kind of beauty. The cosmic speed limit may frustrate our science fiction fantasies, but it also holds the universe together, ensuring that events unfold in a consistent, comprehensible way. It's not a barrier to be broken. It's the framework that makes everything possible. When you trace everything we've explored, from Maxwell's first equations to Einstein's revelations, from time dilation and length contraction to entanglement and the expanding cosmos, you find a single thread running through it all. The speed of light is not just a number, it's the foundation of reality. It's what keeps time ordered, space coherent, and causality intact. Without this limit, the universe as we know it couldn't exist. It's tempting to think of the speed of light as a frustrating barrier, something holding us back from the stars. But in truth, it's the reason there is a stable, predictable universe for us to live in at all. The cosmic speed limit isn't a wall, it's a framework, an invisible architecture that holds the story of existence together. If objects or information could move faster than light, the very structure of cause and effect would collapse. A signal sent faster than light could reach its destination before it was ever sent. A cause could appear after its effect. Time would lose its arrow. The sequence of events, the before and after that give reality its meaning, would dissolve into paradox. Every moment could bleed into every other. The universe would become a tangled web of contradictions where no consistent history could exist. The constancy of the speed of light prevents that chaos. It enforces a universal order, where causes always precede their effects. It's the speed at which influence travels, the pace at which the universe updates itself. Every change, every interaction, every bit of information moves within that immutable boundary. Light speed is in essence the pulse of reality, defining how quickly the cosmos can communicate with itself. It also shapes space-time itself. Because of this limit, time and space are not independent.
They're intertwined into the four-dimensional fabric of relativity, where motion through one affects motion through the other. It's the reason clocks slow down when you move quickly, why distances shrink at high speeds, and why the geometry of the universe bends around massive bodies. The speed of light is the conversion factor between space and time, the rule that gives the cosmos its geometry and rhythm. Even the deep symmetries of physics, the ones that make the laws of nature consistent everywhere, rely on this constant. It anchors the equations that describe electromagnetism, gravity, and quantum fields. It defines how energy and mass are related, how space curves, and how the universe evolves. Without the fixed value of c, these laws would unravel, and the universe would be an incoherent blur of mismatched times and disconnected events. And far from being a dull limiting rule, this constraint gives rise to wonder. Because nothing can go faster than light, everything experiences time differently. Each particle, each person, has its own rhythm of existence, its own flow of moments. This is why time is personal, why simultaneity is relative, why your now is not mine, and why every observer sees their own version of the universe that still fits into the same grand design. The cosmic speed limit also allows the universe to evolve in a stable, comprehensible way. Stars form, burn, and die according to predictable sequences, because information and energy can't propagate instantaneously. Galaxies cluster under the slow pull of gravity, light from their earliest moments still reaching us billions of years later, carrying a record of how the universe began. Without this delay, without this limit, we would lose the history written in starlight, the ability to see the universe as a narrative unfolding through time. And so what began as a mystery in Maxwell's equations and matured into Einstein's cosmic constant turns out to be the very backbone of order in the universe. The speed of light ensures that the universe doesn't dissolve into contradiction. It draws the line between possible and impossible, between before and after, between cause and effect. It is both the limit and the logic of reality. Perhaps that's the deepest truth of all. Limits are not always constraints. They are structures. The laws that hold us back from the impossible also hold the universe together. The fact that we can't exceed the speed of light means that reality remains self-consistent, intelligible, and beautifully woven. It ensures that time flows forward, that history can exist, and that the story of the universe can be told.
So the next time you see light travel across a room or watch the sunset painting the sky, remember that what you're witnessing is not just illumination. It's the rhythm of the cosmos itself. Each photon moving at the universal limit is a reminder of the order that makes everything else possible. Light doesn't just reveal the universe to us, it defines it. The speed of light is not the universe's restraint. It is the universe's coherence. It's the reason we can speak of past and future, of cause and consequence, of meaning and motion. It's the cosmic tempo that keeps everything in harmony, the heartbeat of reality itself. And maybe, in that sense, the most wondrous truth about the speed of light is not that it limits us, but that it lets us exist at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.